So at the end of this, if I do the at operation, I store this whatever the username and the corresponding password, which is a hashed value of that fixed hash value, and that is what I maintain in the table, the username and corresponding hash value. Okay. One of the issue with this value is, as we discussed in this case, if the user 1 and user 2 select the same password, let's say user 1's password is XYG and user 2's password is also XYG, and then when I pass this to function yep, it generates the same output, maybe 1 2 3, and when I pass this to this function, again this generates the same hash value 1 2 3. Now the file itself is looking like this. You have got the user 1 and user 2, and the corresponding, the first column is the, as usual, the username, and this is the hashed password of the one. So here you have got 1 2 3, and here also you have got 1 2 3. So this file is not encrypted, it is in the plain text format. Now if let's say user 1 wants to log in, so he supplies its username and password, and as usual you take this user u1 is in the plain text format, you can go and check whether it is a valid user, and you take this password and then pass it on to the function yep, and then whatever the output that get generated, you go and check whether what is the word. And similarly, if you just look at the or screen the this file where the username and the hashed passwords are stored, I can see two passwords having the same value. So if the user 1, instead of claiming to be user 1, if he is claimed that user 2 and supply the password P1, then also he can actually log in, because once this passed to function yep, then also he can actually log in because it produces the same hash value. So this is another issue. If I maintain the passwords as hash values, and if two hash values have got the same two entries within got the same hash values, then one user and the other user's password can be verified with the same thing. So this becomes another issue. So user 1 and user 2 probably by just looking at the entries of hash values, they might have chosen the same password. So although 1 2 3 not necessarily be generated by the same input, two different passwords can also generate the same password, but just by looking at the values itself, 2 3 itself might give you some idea. So probably user u1 and u2 might have chosen the same password. How do I actually avoid such situation, giving hints to the users that two different users might have chosen the same password? So this is done with something, a mechanism called as the salting. So what exactly happens in the salting is, you don't hash the password as it is, you generate something called a salt. This is actually a random number. You take the user password, let's say user 1 has got the password P1, you take this password, concatenate this with the random number. So P1 concatenation with the random number, which is the also the salt value. You these two values together you give it to the function yup. So by adding a random number, even the P1 selected by the user 1 and user u2 also, let's say select the same password P1, as long as the random number generated for the user 1 and user 2 are different, when I concatenate these two, the input to the function yep look different. So in that case, for the user 1, the password, the hash value that get generated might be 1 2 3 4. For the same password chosen for the user u2, and as long as this component is different, the function f might generate the different value, might be 989. So these are two different hash values. By just adding this random number, you have actually avoided that situation of two different users to having the passwords having the same hash values in the password file. So that is what the concept of the sorting. Now the question is, how do we actually generate this random number? Random number generate, there are a lot of good random number generation functions are there. The way they operate is, you take the reference clock value as a reference, the current time, and then you give it to some other function, do some mathematical operations and derive some number. So that number is actually used as a random number. That is exactly the salt value. The earlier versions of the Unix systems used 12-bit such random numbers. So you, irrespective of what is the password length, you generate a 12-bit random number, concatenate that with the password, and then give it to the the function f, and then you generate whatever the hash value that it generates, you take and then go and store inside the password file. So that is exactly what is done. So by doing this, I repeat, by adding the salt value, what exactly happened is you avoided the situation of having the two different users having the same value, assuming the number of users are small and random numbers are generations are different for each user. So you will have two different users having the two different passwords. So thereby you actually avoid that situation of having same hash values for two different users. Now let's took a specific example of how exactly the Unix system or the Linux system manages the passwords. The at least the Unix system actually stores the password in a particular file called /etc/password. This is an earlier version of the Unix systems, and the hashed values are stored in this particular file. So it does it uses the sort values and also it does the hash value. The way this function actually works is, the following steps are used. You take the ASCII value, 8 character ASCII values, all password zeros, and then encrypt that with a key generated from the user password. Remember, user password is used as a key. That key is 56 bits in length, and the input is all zeros, which is up to 64 bits. And then you encrypt with the version of the DES. So this crypt function was used. Crypt function is an implementation of one of the popularly known encryption algorithm called as the DES. So you give this to as input to this script function, and whatever is the output that get generated after the 25 iterations is the hash value. Use that as a hash value. So let's maybe write here what is the function. The all zeros, 64 bits, all zeros. This is my one input. These are 64 bit. You take this as one component, and the function f, whatever hash function, here it is the crypt function, and the second component that is the key. The key k is generated from the user password. The way it is generated is, let's say again go back to the previous example. If this is the password, you convert every character, ASCII character, into binary number. So maybe 0 1 0 1 1 0 1 0 0 is corresponding to n, and then similarly for E also, this is your n. These are some hypothetical numbers, don't take that as 1 1 0 1 1 0 1 1, something like that. So similarly, whatever the numbers of the characters are there, so if the input password is of length more than n, you use the first 8 characters for generating this key. So you ignore the first bit or the most significant bit within this binary sequence and take the remaining 7 bits from each of the characters. So if the password is more than 8 characters length, then you truncate it, you use only the first 8 characters and take the 7 bits from each of the character, concatenate it, that will give you at the end of this. So 8 characters, 7 bits from each, 56 bit key. So use that 56 bit key for this encryption. On the other hand, if the password itself is less than 8 characters, then you put leading zeros, make it 8 characters, then again do the same thing. So ignore the most significant bit and use the remaining 7 bits, concatenate all the bits, generate the 56 bit key and use it for encryption. So the same key, this is the iteration number 1. Let me write here, iteration 1. So similarly, whatever the output that get generated, use that as input to the next is. So same crypt function and then the same 56 bit key, do the second iteration, continue this operation. How many times? 25 times. At the end of this, after the 25th iteration, whatever the number that get generated, that is your hash value. This is what the Unix systems or the Linux systems actually, nowadays a variant of this is used, but with the original algorithm was something like this. So this value is, the final value is actually stored in the password file, where in this /etc/password file. So this is how the Unix systems actually generate and manage the password. So when you want to verify, what you need to do, you need to take the user password, again do this binary conversion, ignore the most significant bit, generate the 56 bit key, start with all zeros, 64 bit number, and then do the encryption 25 times, generate the hash value, take that hash value and go and check what is the stored hash value in the password file. So that's all the verification is. So now the question is, second thing, we said that the password itself is not the only thing that is used, but salt is also used. So you use the password and the salt together for the encryption. So if salt is used for the encryption in the DAS algorithm, you need to maintain that salt value also, the random number also inside the file, so that when you generate the key or give the input to the function, you also know what random number used for what username. So the table itself might look like something like this. The user ID is the first column, and then the plain text salt value, and then the password. This password is the hashed password, hash value. So this is hashed. So now the function, the crypt function what we are talking, is not only taking the one input, the password, but also the salt value. These two are taken, and again some form of the operation is done. You encrypt all zeros and then generate a hash value, come back and store in this password file. So how does the verification happen? Again, you go and check when a user tries to log in, you take the input password and go to this file, check what is the plain text salt value, take that salt value and the user password together, you give input to this function. Crypt 3 is an advanced version, later version of the crypt function that we were seeing here. So there were different versions. Original was crypt, and then the version number 1 and 2 and then 3. This is the third version of the crypt, which takes these two values, which is the salt and the password as input. Some operation is done inside, and then a hash value is generated, So they take this hash value, go and check in this corresponding place, whatever is there against that username. If these two matches, then the user is allowed to log in. This is what the operation happens inside the Unix or the Linux systems. Crypt 3 is again kind of a bit old function. Nowadays, the Linux systems use different async algorithms. We will see that in the next couple of slides. So, this is exactly what happens inside the verification and management process. So, now let's take a look at where exactly at least in the modern Linux systems, these passwords are maintained and what all other information is there inside those files. I said that the password, the hash values and the usernames are stored inside the password file, but the modern systems don't store the password in the /etc/password file. Now they divide the entire operation into two different files. One is the password file still that is there, and there is a concept called as the shadow file. The actual passwords are nowadays not stored in the password file, but it is stored in the shadow file, here in the shadow file. So then the usernames are maintained inside the password file, but the actual passwords are there in the shadow file. So let's take a look at what exactly is there in the password file and what exactly is there in the shadow file. The password file has got rows. For each user there is one row. So for example, root is one user, there is one row corresponding to that root user. Daemon is second user, and for that I have got another row, and so forth. So each row has got these many number of the entries, particularly the username, password, user ID, group ID, user information, home and cell. So these entities are separated by columns. Every time you have a column, so that becomes the end of the one component. So for example, if we take one particular row, so here in this case, S is the username, X is the password, assume that is the password for the time being, and then this is the next three is the user ID, group ID, and some information about that user. So any information that could be some verbal description about that user. So here is the system user, something like that, and then the home folder corresponding to that username, and then the last column indicate what is the cell that is given to that user when he or she logs in. So for example, if you see look at the root, then this /bin/bash, the bash is the cell that is given to the root user, and some of the usernames have got no login written at the end. No login means that user cannot log in using that username. For example, sys cannot be used to log in. There is no cell that is given to the sys user. These are all system users. Normally the system users which the operating system uses to manage different operations, such users are not for login. But for there are other users, if let's say some username somebody XYZ is there, that XYZ can be used to log into the system. So that differentiation is there. Whenever there is user is allowed to log in, then there is a cell corresponding to that, and when the no login is written, that user is not allowed to log in. Now let's come back to the case. I said that the password itself is nowadays not maintained in the password file, and the indication that the password itself is not in this particular file is denoted with the letter this X, whatever in all the places you see the letter X. So X means that the password, the actual password itself is not in this password file. Historically it was in the same place, in this place, but now it is in the shadow file. So it indicates that the actual password in the shadow file. The shadow file also, if you look at the structure of the shadow file, there are rows, one row corresponding to each user. Whatever the usernames are there in the password file correspond for each username, each row there is a corresponding row in the shadow file as well. Every row is again divided into the multiple pieces, and each component of the O is again separated by the column, and the details of what all these different columns indicate are here. So the first column is the username, the second column is the one which is actually having the actual encrypted password. Encrypted password means the hashed password of the user, and then the remaining some of there are times, elapsed time. So when was the last time the user has actually changed the password, and what is the validity of this password, when the due date, when the password is actually due to be changed. If before the change, if we want to warn the user, let's say password expires after 1 week, 1 week before that you tell the user that your password expires, that is called warning date. So you set some timer, when the password expires, before that you give the warning, and then there is a expiry date to that particular password that is there. And then if the password has expired, since when that user account, that password has expired, that is a disabled time. So all these timers are there inside the rows, so you can use this, and the last column is actually used left open for future cases. So out of these timers are, I think, self-explanatory. The two things which are of interest to us is this two things. One is the username and the encrypted password. So if you look at diagram, the user one, the last user here, the second column, whatever is here between this to this is the place where the actual password of the user one, the hash password of the user one is stored. So this password and hashed password is again divided into three components. Each one is separated by this dollar symbol. So in between whatever this dollar symbol, this dollar symbol is one component. The second component between this dollar symbol to this one, and then the third component from here to here. So this is the thing. So the interpretation goes like this. The first part is an index to the kind of the hashing algorithm that is used. So meaning, if the number here is 1, that means that the hashing algorithm that is used is MD5, and that generates the 22 character length of the hash value. So here in this example case, the number is 6, that indicates that the hashing algorithm that is used to hash the password is SHA 512. This is the 512 bit hashing algorithm that generates the 86 character length hash value. So just to save some space and for reference, I have not put all the 86 characters here, but a number, alphanumeric number, which is looking similar here. This is the actual the hash value of the password. And the second component indicate that the random number that we are referring to, the plain text salt value corresponding to that user is actually stored, is the second component here. So this is how exactly the passwords are maintained. I repeat, the first value is the index to the algorithm, second component is the actual plain text hash value, and the third component is the actual hash value corresponding to that password of that user. Okay, so that is how the Unix systems actually or Linux systems actually manage the password. We can actually take a demo of that one by logging into a Linux system. I'm here at this last etc directory, and let's open the password file. So this is the file name. So once I hit enter, this file is opened. So you can see there are large number of the users, and then one row for every user, and there was whatever the elements that we discussed in the previous slide. So all those things are actually there: the username, the password, the UID, GID, some description about the user, and then the home folder of that user, and then the shell that is given to that user. So normally these users, so many of them are system users, and there are no logins allowed.
but only for this user this is allowed to log in. This name is allowed to log in, and then the corresponding home folder and the shell that is given, that is shown here. So this is about the password file. As I said, X indicate the password is in the shadow file. So now let's close this file and open the shadow file. Okay, this is the file, and you should see again the corresponding whatever the usernames are there. For them, you got the password entries here, one row for one user. And similarly, the last user Neminath has got this one. The Excel password is actually here, and this is again divided into three parts as we discussed. And one thing that I forgot to list, there are some wherever the password is supposed to be there, there is an exclamatory mark and star mark. Both of them indicate that the user cannot log in. There is no password set hash value that is calculated, and you cannot use that username to log in. The only difference between this explanatory and star is that permanently that user is not allowed to log in, but an exclamatory mark is currently there is no login set, there is no hashed password stored here, and that username cannot be used to log in. But in future, if you want, you can set a login, you can enable login for its user. That is the only difference. So let's close this.
So after having seen the demo of the password file and the shadow file, I want to end this discussion on by taking some examples of how you can actually mount an attack, password cracking attack on the systems, on the authentication methods. There are different ways of doing the attack. The simplest attack is something called as the dictionary attack, and there are two cases here in the dictionary attack. One is when the salting method is used, that time how do we crack the password. Second thing, when there is no salt involved, then how we crack the password. So in the dictionary attack, what I have is, I have a file. This file contains the commonly used words or commonly used passwords. What are the likely passwords that are used in the system in any password by any user? You compile that list and make it a file. So here 2003 is one entry, passes the second password 65. These are all the possible passwords that you think are likely to be used by some users. So you have got a hashing algorithm, whatever the choice of the hashing algorithm. This is our function F. You take one word and then pass it into this hashing algorithm. So in the absence of the salting, one word generates one hash value. The second word generates the second hash value. So like this, you can compute the hash values corresponding to every entry in the dictionary file, and you take this pre-computed hash values, then go and check if you get access to this password file, whether any of these pre-computed hash values match with any of the hash values stored inside this file, password file or the shadow file, whatever you want to call it. So this is hypothetical. So if let's say user 1 has got the hash value A9Y U0, and this is the one which is actually matching this hash value, you go back and check what was the keyword that was used to generate this hash value. That is the password of the user 1. So I repeat, what you have is a pre-computed set of the hash values. You take these pre-computed hash values and then go and try to match with on one-on-one basis for the password file. So if any of the hash values of these pre-computed hash values match with there, then you go back and check what is the word that is used to generate that password, and that becomes the password. You have cracked the password. This is the case when sorting is not used, when random number is not used as an input to the hashing algorithm. If on the other hand sorting is used or random number is used as an input, then the scenario slightly changes. On this, I still have a file containing the possible passwords. These are the commonly used passwords, dictionary of the passwords. I'm guessing that these are the one of these should match with some username passwords. So now the scenario changes depending upon the length of the salt. Let's say the earlier versions of the Unix used 12-bit salt value. Now I don't know what is the salt value corresponding to user 1. So what is the salt value corresponding to user 2? Then how do I pre-compute the hash values of these words? So the only way that you can do is, so you take the 12-bit salt value for all possible values of the 12-bit salt values. You take for one dictionary word, you systematically generate all possible combinations of these 12 bits of the salt value, and then give that is the hashing algorithm as an input, and whatever the hash value that you generate, you come back and store. So for example, for the word 2003, for the 12-bit, one possible combination of this 12-bit input, this is the salt hash value. And for the different combinations of these 12 bits, and for the same word 2003, you will might have a different hash value. So like this, if I guess what is the length of the salt value or the random number value, how many bits are there, 2 to the power of those many combinations. So 12 bit, the possible combination is 2 to the power of 12. For those many combinations, for one word, those many hash values are there in this pre-computed list. You can think of now. So larger the random number size or the salt value size, larger the number of the entries for every word in the dictionary, 2 to the power of those many number of the different hash values are there in this file. This file would be much larger now. Now how do I do the verification? Again take this pre-computed hash values and go and check in the last column here if any of these hash values in this column actually match with the pre-computed hash values here in this file. Then you know what is the salt value that is used, and then if that salt value matches with the salt value that is here, and then corresponding to that, what is the password, that the word that was used to generate this hash values. These two combinations together will now define the how the password is actually matched. Now you have cracked the password. You take the salt values here from this column, and then the hash value from this one, you match it, and then you go back and check what is the word that is used. So that is how the passwords are checked. This is the dictionary attack. The second way of attacking the authentication based system is using something called as the brute force method. So in this case, only the difference between this and the previous case is, in the previous case we had the dictionary of probable passwords. In the brute force case, I am not generating the I am not taking the input from one particular dictionary or file, but I am systematically generating them. So I start with one letter combinations first, one digit combinations, and then two letter combinations, two digit combinations, one letter, one digit combinations, and so forth. So here in this case, all zeros to from all nines to G, all these are all possible combinations of the letters and digits. So you take these as input, and then again supply that input to the hashing algorithm and generate the hash values. Again, if it is not salted, then you don't have to use every word that is generated here will result into one entry in the pre-computed hash value file. So if it is sorted, then you will have that scenario for every possible combination of the digit of the sort value. You will have one possible hash value for the one word here in this case. So same thing happens. The only difference is with respect to the previous one is here the passwords are not taken from the file itself, but they are generated systematically. Again, as you say, if you use the sort value, then for one possible combination, one value, possible value of the sort value, you will generate one hash value. For one word in the brute force trial, you will have 2 to the power of those many number, whatever, the 12 bit, or if you use 24 bit sort value, 2 to the power of 24 combinations. Those many number of the pre-computed hash values are there. And again, you comparison would be same thing. So you compare both the sort values and the corresponding passwords together. If there is a match, then you crack the password. So these are the two popularly used password cracking methods. Of course, there are other more sophisticated methods like rainbow tables and all. So I will not go into the discussion of that. With this mechanism of how the memory management is done by the operating system and how the user accounts and passwords are managed within the operating system. Let's end this discussion here. Thank you for joining.